All right, let's take a look at this problem together. It says a heavy wooden block is dragged by a force F along a rough steel plate, as shown below, in two possible situations. The magnitude of F is the same in both situations, okay? And the magnitude of the friction force in this one compared to the first. So is this one bigger, smaller, the same as the other one, as in case 1? So which one's bigger, case 2 or case 1? All right, so what are we trying to do? Well, when I look at this problem, first thing I want to do, if I'm dealing with friction forces, I'm going to start drawing free body diagram. So I'm going to draw a free body diagram for this guy. It has a weight force down. It has a normal force up. It has an applied force over. And it has a friction force in the backwards direction. Assume both of these have coefficient of frictions of mu. I know that my friction force then is mu times my normal force. And I can see in this case that because of the y direction, we use a standard coordinate system, because of the y direction, my normal force minus my weight force have to be equal to 0. It's not moving in the up and down direction, so my normal force is equal to my weight force, which means this is going to be mu mg. So my friction force for the first case is mu mg. Now I want to know what is the value for this one. I'm just going to assume I'm going to need a theta in here. I don't know what theta is. It may depend on the angle. It may be always for a case, but let's see how the free body diagram for this one looks. And I'm going to put it down over here, and let's actually do this in a different color. Probably we'll use blue for this. So if I look at the free body diagram for this, I have the applied force up the ramp. I have my weight force down the ramp, or down into the floor, goes straight down. My normal force points perpendicular to the ramp, perpendicular to my applied force. And my friction force, because I'm moving up this ramp, I'm going to assume I'm going to have a friction force down the ramp. And again, in this case, it's mu times n. It's just the definition of friction. So in this coordinate system, I'm going to say x is up the ramp and y is perpendicular to the ramp. So in the y direction, I get that the normal force minus mg cosine of theta. Theta was that angle over here again. Cosine of theta, because that angle is theta right here, is going to be equal to 0. Same reasoning over here, that my weight force, or whatever is pulling into the ramp, is being countered by pushing out of the ramp, because I'm not lifting off the ramp or moving into the ramp. So that means my normal force is equal to mg cosine of theta. Well, I really only want to compare the friction. So what is the friction? I have one friction up here. I need to figure out what the friction is down here. And I know that my friction is mu times normal force, which is mu mg cosine of theta. So in my second case, mu times my normal is equal to mu times mg cosine theta, just substituting it in. And I will see that this is mu mg, this is mu mg cosine theta. So I have to ask myself, on the ramp, how does this cosine of theta apply? Well, first off, I know it's not the same, just because I have that cosine term. Can be greater than, less than, or equal depending on the magnitude. That's not right. The only thing that's different between these two equations is the cosine of theta. And what else? Greater than, less than, or less for some angles, greater than some angles. So at this point, we don't know the difference between these three unless we know something about cosine. We know that the cosine of theta will go between 0 to 1. So at 0 degrees, the cosine is 1, and at 90 degrees, the cosine goes to 0. So this number is always going to be equal to 1 or less, which means that 2 is always going to be less than 1 if there's an angle, assuming angle is not equal to 0. The other thing that we should have probably checked at the very beginning, but because the thing is being moved, we're in a kinetic friction. So we really are dealing with a kinetic friction here. So our applied force doesn't come into play because once we move into kinetic friction, for both of these cases, then we deal with a constant friction force, mu times n.